So let's take a look at number 19, rangeBitCount. Let's see what it's asking us. All right, so we're given two numbers, A and B, where in this case, they're both greater than or equal to 0, so they're non-negative numbers. And we also know that A is less than or equal to B. Okay, now we want to construct an array of all the integers from A to B inclusive, so including A, including B. So just keep in mind, in the case where they're equal, there still would be one element in the array. So this array that we're constructing is going to have at least one element in it. Okay, and now we need to count the number of ones in the binary representations of all the numbers in the array. Okay, sounds like fun. So basically what we want to do is we want to go through each of the numbers. So we'll do something like, I don't know, for let n be assigned the value of A, n is less than or equal to B, n plus plus. Okay, so this is going to go through all of the numbers, starting with A and finishing with B, including B. Right, because it's an inclusive range. So basically what we want to do is something like this. We want to have some sort of, let's say, sum value over here that we're eventually going to return. And at each step, we're going to say sum is going to be, we're going to add on to the sum. What are we going to add on to the sum? Well, basically something like this. We'll say one count of n. Okay, so this is basically going to be the structure of our solution. Just like in the other ones, we're probably going to look at this in a few different ways. But overall, I think we're generally going to maintain this structure. Okay, so at this point you might be wondering, what's one count? It's green, we don't recognize this, you didn't mention this before. You're kind of surprising us with this. So, blindsiding us, that's the word I was looking for. Okay, sorry about that. But anyway, let's make it now. Let's do the function one count. So this is just going to be another function within this function. Or I suppose, you know, it doesn't have to be. Like, one count could live outside of rangeBitCount. It's fine, it doesn't matter. I think probably it's fine just to keep it in here, keep it within the scope of rangeBitCount, because we're not really going to use it for anything else. So what's it going to do, I guess is the question. Well, it's going to count the number of ones in the binary representation. Now, like we've seen in some of the previous one of these bit challenges, right, the corner of zeros and ones challenges, what we've generally been starting with is something that looks like this. You know, we generally start with this kind of thing. num.toString with an argument of 2. That is going to give us the binary representation of the number in the form of a string. So we'll start with this, and then we'll try to come up with a more clever way of handling this afterwards. Okay, so, you know, we could say something like this. Let str be assigned the value of num.string2, or instead of just string, let me just say bin, okay, because that's sort of like the binary representation. And then maybe we'll put that in the form of an array. So we'll say let array be bin. Okay, so this is the way I usually like to do it. Keep in mind there are some other options. We could do a dot split. We could do an array.from. But I like this way. It's you know, the most efficient in terms of the number of characters, but also I think it looks pretty neat. You know, it's just like a new array with the characters of this thing all spread out. All right, and now what we basically want to do is we want to find the number of ones inside this array. So how many are there in the array that are ones? So one way we could do this would be to use a filter. Now, we talk about maps, we talk about reduce, like pretty often, we use those a lot. But filter is kind of like, you know, it's the third sibling that we don't really see much of. It's like the middle child, you know, it's like kind of weird. And anyway, the point is, so we're going to use filter now. Now, if you're unfamiliar, the way filter is going to work is it's going to take in a function, just like map or reduce. What this function is going to do, I guess I'll just call the input a character, right? Because it is a character in the string. Or, you know what would be even better? Let's call it a bit, because that's even more relevant to what we're talking about here, right? So then we'll say, well, is the bit equal to 1? And then basically, this is a Boolean, right? So this is either going to return true or false. If this ends up returning true, the element will stay inside the array. If this ends up being false, the element will not stay inside the array. So let's do a little example here. Let's say return one count of 7. And I think this should give us 3 ones, an array containing 3 ones currently, because 7 is just 1, 1, 1. Yeah, there we go. Okay, let's think of another number. Let's say 5. 5 would be 1, 0, 1 in binary. So I'm expecting to get just the 2 ones back because it should filter out the zeros. There we go. So basically, here, let me even do this. Actually, you know what? Let's build a little bit of structure around this. So we're going to have a number. We're going to call it x. And in this case, it's 5. And we'll do a console.log of x.toString with an argument of 2, so basically the binary representation in the form of a string, and then we're going to return the 1 count right now. So basically, here we go. We've got 101, that's 5 in the form of binary, and we're returning 1 and 1 there. Okay, let's just look at another number over here. We'll see, yeah, okay, so 1, 0, 1, 1, and we're just getting the ones here. But that's not really what we want. We don't want, like, all of the ones here. We want to just know how many of them are there. So instead of just getting 1, 1, 1 here, what we should be getting is 3, which happens to be the length of this thing. So maybe I can just do a dot length on this and call it a day. Let's see, would that work? So in this case, since 11 is, what was it, 1, 0, 1, 1, we should get 3 for this because there are 3 ones in its binary representation. And we'll be able to verify that by looking at the console log. So yeah, it says 3, we've got 3 ones here, and I think that's pretty good. Let's try the number 2, that would be 1, 0, so it should have 1, 1. So yeah, we're getting 1 here, 1, 0, that's great. Okay, any others here we want to test? Are we convinced? Should we try like a big number? Let's do just like 1,000. We'll see what we get for that. So that's 1, 1, 1, 1, 1, 0, 1, 0, 0, 0. And so yeah, there are 6 ones in there. I think this is working pretty good. I think our 1 count is giving us what we're looking for. So, okay, let's see. I guess we might as well just go ahead and test it out with this. And what we'll find is, yeah, it's passing all the tests here. It's giving us what we're looking for, no problem. Okay, good stuff. Now, could we make this a bit better? Well, yeah, I think so. I mean, again, I'm not a big fan of like these sort of one-liners, but in this case, it feels, I guess, kind of merited. I don't know if it's really worth it to, whoops, not what I wanted. I don't know if it's really worth it to be declaring all these new variables for things that we're just using one time. So like, whoops, what happened here? Oh, yeah, okay, so that was array, so I wanted to replace array with that. There we go, that should work, right? I think? Let's find out. I mean, we could even at this point, yeah, that's working. At this point, we could even turn this into like an arrow function. You know, we could say something like const 1 count is assign the value of something that takes num to this other thing, which is all that. You know, and that'll still work. It's even more of a one-liner now. In fact, it's kind of awkwardly long. So maybe I'll turn it back to what it was before when it was a function. Yeah, I think that's good. Let's run that. And there we go. Okay, so let's just make sure it's passing all the hidden. So let's try running the hidden tests. And we'll see what happens with that. I might as well just copy that while we're here, because we're going to start a new, yeah, there we go. So that's working. Very nice. Okay, we're making a dent here. We're like, I guess about a third of the way through, more than a third of the way through, 38% of the way through the corner of zeros and ones. So that's nice. We'll continue with that. Whoa, okay, sorry, that's not what I meant. Okay, so let's get back in there. And we have unfinished business. All right, so what I wanted to do is paste that in and put a big old 1 next to that one. Okay, now, like I said, this stuff, everything we see here, is probably going to stay more or less the same for all of what we're going to do here. But I do want to sort of restructure this in a little way, because if you think about it, I mean, we're looking at a situation right now where basically we have this 1 count function, right? So for every number we try to feed in here, it's going to take that number, it's going to convert it to a string, a binary string specifically. It's going to spread that out into an array. It's then going to run a filter on that array, so it's going to go through the whole thing, and then it's going to measure the length of it. it's kind of inefficient, if you ask me. I mean, I don't like the idea that we're cracking open a new array every time we want to count the number of ones in the number. It feels like that's memory-wise a little bit inefficient. Now, something I should probably mention is, if we take a look at this, the constraints are really, they're fair, you know? Like, we're not going to have to worry too much about having numbers too big here. Like 10. 10's the biggest number. I would definitely prefer for this to be something like a 10,000 or something like that. I think that would give the problem a bit more of a challenge. So that would be nice. But anyway, I suppose we could always do a custom test here. You know, you could always build in a big one if we wanted to. In fact, I don't know, would that be fun? Maybe we should do something like that. Let's put a 2 on this one, bring this guy back, run that, and we'll just verify that that's still working. I guess in the meantime, oh no, I guess we can't do a custom test. We'll think of one in the meantime. So maybe we want to go with A and B values that are like really big, and I don't know what the actual answer. So yeah, that's working. So let's just go with A value that's like 100 and a B value that's like 10,000. And output, I don't know. Let's do an estimate. Let's say it's 1. So that's probably going to be wrong, but the question is it going to work? Okay, so that's the actual answer. We might as well edit that, right? Get that answer in there, just so it's passing the test. Okay, so that's surprising, I guess, actually. I wasn't expecting it to work necessarily for such big numbers. If we were to maybe put another 0 on the end of that, would it time out? It's still not timing out, so maybe this is better than I thought. Let's put this in. We'll keep this for now. Yeah, we'll keep the custom test just for fun, I guess. So we'll put the 1 back on that one. We'll remove the 2 from this one, and let's just put something in there real quick. So this should not produce the right answer. Yeah, okay, it's not producing the right answer. That's what we want for now. So what are we going to do with this? Well, we want to find a way of doing this 1 count that doesn't involve converting to an array, you know, doing like a 2-string, any of that kind of stuff. So we're going to use a recursive method here. Okay, so there's something I want to point out just in terms of these binary numbers, in terms of how they grow and stuff like that. So let's grab a nice color. Okay, so let's say we're, how should we do this? Okay, let's say we're looking at a number, maybe it's 11, right? So I think 11 was this one. Yeah, okay. So if we were to divide this one by 2, okay, rounding down. So 11 divided by 2 is going to give us 5 if we round down. Technically 11 divided by 2 would be 5.5. If we take the floor of that, we would just get 5. Now as it turns out, 5 is 1, 0, 1. Okay, so basically what we're able to do is we can say, well, this compared to this, we've basically just right shifted it, right? Let me grab another color here just so we can put some additional notes. So this is 11 in decimal. This is 5 in decimal. And basically what we've done is we've done one little right shift by 1. I'm not sure if I said right shift or left shift earlier, but anyway, what I meant was right shift. We've shifted it to the right by 1 unit. And of course, that caused this 1 here to disappear. Now, I want to contrast that to another case here, which would be, let's say we had like 1, 0, 1, 0. Okay, so that would also get right shifted to 101. That would represent the number 10. It would get right shifted to give us 5. Now, basically the difference here is that the 10 had a 0 here already. It didn't have a 1 there. So when we did the right shift, we didn't lose any information. We didn't lose any extra 1s. The number of 1s that 10 has is the same as the number of 1s that 5 has. So what I'm trying to say is if we were to right shift it by 1, or in other words, if we were to divide it by 2, taking the floor, right, round it down. So if we were to divide it by 2, then what we would find here is that Well, okay, yeah. So we Math.floor divide by 2, and either we're going to have the exact same number of ones, or we're going to have one fewer one, and it's this one right here. So basically, all we need to check is, well, does it currently have a 1? You know, like in the least significant spot, does it have a 1 there? In other words, if we were to divide this number by 2, would we have a remainder of 1? Like, if we take this number mod 2, do we get a 1 or do we get a 0? Okay, so 11 mod 2, we get the 1. 10 mod 2, we get the 0. Let me try to show you what I mean by this, okay? So basically, what I'm going to say for this one count is if num is 0, then we're going to return 0. Otherwise, if that doesn't end up being the case, we're going to return num mod 2, okay? So basically that was on the end of the 11, we had that extra 1 in there. On the end of the 10, we didn't. Okay, so we're going to have num mod 2, and we're going to add to that the 1 count of what we would get if we did a Math.floor of num divided by 2. Okay, so let's see if that works, first of all. Yeah, it works. Okay, cool. So that's nice stuff. Did it pass that? Yeah, it passed that one too. Okay, I'm surprised. All right, so we'll submit that, and great, that's working nice. So then let me take this again because, you know, we're here in the corner of zeros and ones. We want to be keeping this sort of bitwise as much as possible, right? So let's take this opportunity to talk about some of the, I guess, coincidences, some of the other ways of expressing the same thing using bitwise operators. So for example, over here, I was saying, num mod 2. I was basically trying to check if the last thing in the list was a 1. You know, so like if we had 11, that was 1 0 1 1. If we had 10, that was 1 0 1 0. And basically the idea is I'm just checking this last character here, this last bit, is that a 0 or is that a 1? Okay, so by doing mod 2 of the number, we'll find that. But really, if you think about it, what we're trying to check here is if we were to put a mask on this, right? If we were to say 0, 0, 0, 1, okay? If we were to do an AND with these two numbers here, what would we get? Well, basically the same thing. Because for all these zeros here, 0 and 1, no. 0 and 0, no. 0 and 1, no. Because these are zeros, we can only get a 0 when we do an AND between these two things. Whereas since this is a 1, well, we have two possibilities. If this one was a 0, we'll get a 0. If this one is a 1, we'll get a 1. Well, hey, that's what we want. So we can just do num and 1. Okay, bitwise and 1. And that should give us the exact same thing. No difference there. Another thing I'm going to say about this, there we go, no difference. Another thing I'm going to say is we're doing this Math.floor of num divided by 2. Now keep in mind, when we were looking at that a second ago, we had something like 1, 0, 1, 1, which got divided by 2 to give us 1, 0, 1. Basically, all of the bits are shifting 1 to the right. Whoops. So let's just do that. We'll say num shifted 1 to the right. Let's see if that works. And it does. Okay, so that's actually a lot nicer. I mean, this one is pretty much the same number of characters. Clarity-wise, I don't know which is better. It depends how familiar you are with bitwise operators versus like modulus and stuff like that. But this is straight up nicer. You know, instead of like Math.floor of n divided by 2, we just say num right shifted by 1. So I think, you know, as long as this makes good sense to the reader, I would say in a lot of ways it's a better way of doing it. Okay, so basically this strategy over here, very, very similar to what we have down here, except we're using bitwise operators now instead of using sort of the more traditional math operators. Okay, so this is good. This is, yeah, this is pretty good. It's getting better, I think, right? So I just have one issue with this one now. And the issue is that, okay, first of all, let's just make sure we have a good understanding of how this is all working. So maybe we should go through it with an example, okay? I don't know what would be a good example number to use. Let's just select a good color first. So, okay. What do we want to use for our example? I guess we've been talking about 11. We might as well just use 11. Okay, so 1, 0, 1, 1. All right, and now basically our question is, we're going to run one count on this. So we want to say, well, is this number 0? And no, it's not. So we're not going to return 0. So what are we going to do? Well, we're going to return num and 1 and add that to one count of num right shifted 1 to the right. Okay, so basically, what are we going to get from this? So we're going to get num and 1. Well, in that case, since there is a 1 over here, we would get 1. Okay, so we have a 1, and we're going to add that to what we would get with one count of our num shifted 1 to the right. Okay, so if we shift it 1 to the right, we'll get 1, 0, 1. Okay, cool. So then what do we get from that? Well, in this case, now we want to run this. Again, is this equal to 0? No, it's not equal to 0. So we're going to say num and 1. Well, that is a 1, so we'll get a 1 from that as well. And we're going to add that to whatever we get by right shifting this one by 1 and then running the function on it again. So, okay, so we get this now. We got 1, 0. Is it equal to 0? No, it's not equal to 0. So we'll move on to the next line. Num and 1. Well, this is a 0, so we actually do get a 0 out of that. And then we're going to add that to whatever we get by right shifting this by 1. So we get a 1 now. And yeah, num and 1, well, that one is pretty clearly 1. It's just 1 itself, right? It's the same thing. So we'll right shift that one. We get a 0. And then we say, is num 0? Oh, actually, yeah, it is. So we're going to return 0. So basically, just to finish up with this one, and I'm running out of room, plus 0. So we say 1 plus 1 plus 0 plus 1 plus 0. We get 3. And that's what we want. 3 is the number of 1s over here. Okay, cool. So this is pretty neat. It's our one count function. It's recursive. So basically, it's using previous elements to do the calculations here, which is kind of neat. But in some ways, it's kind of not neat as well, because the issue I have with this is basically the following. What if my next number, what if I was going to have, like, let's say 1, 0, 1, 1, 0. Okay, what if I needed to calculate this one? Well, basically, if I wanted to go through this number, I would go through this whole process. I'd say, okay, so this is going to be 0. You're going to add that to the result of this one. There's going to be a 1 plus, et cetera, et cetera, et cetera. You know, I'd go all the way down to 0 every time. Maybe then I'd have a number bigger than this. I'd go all the way down to 0, even though I've already calculated all of these, right? That's the issue I have with it. We already know what one count of this is, so why bother going all the way down here and repeating these steps if we already know what it's going to be? Okay, so this is bringing us to kind of a new concept. This is, it's in line with the concept of backtracking, dynamic programming, that sort of stuff. It's in the same family as those kinds of techniques. I believe the technique I'm about to use is called memoization. Okay, so I'm going to write that down. Memoization. Not momoization, memoization. Okay, memoization. Now this is a really strange word, and I would say this is one of the most common words for autocorrect to pick up. You know, like, try typing this into Microsoft Word. You won't get past it without it changing it to memorization. Or at least that's been my experience. So it is a word, and basically what it means is, well, it's kind of like every time we discover a new value, every time we do a calculation, we're making a memo of that. We're making a note of it. We're saying, oh, got it. We've got a new value. We're going to keep that one in mind so that the next time we need that, we already know what it is. Okay, so basically the way we're going to do this one now using our memoization technique is we're going to do a new array, and it's going to be called ones, okay? And it's going to represent the ones that we already know. Now, if you take a look at this, we're saying if the number is 0, return 0. So I might as well just put that right in there, okay? Now we have our ones, and it's basically just a 0, and yeah, that's the one that we know. So here's what I want to say. If num is in ones, well, in that case, we're going to return ones at num. Okay, I want to clarify this statement a little bit. So what do I mean by this? So first of all, ones, it's just an array. Currently, it just has 0 in it. Maybe we'll add more to it later. But if num is in ones. Now, keep in mind, what I don't mean by that is if 1 includes num. Okay, so I'm not trying to say if num is an element of ones. I'm trying to say if num is one of the indices of ones. Okay, so this is This is an area of potential confusion here. The in does not mean that num is an element. It doesn't mean it's a value in the array. It means it's a key in the array. That's really, really important. And because it's a key in the array, it means I can do this, okay? So what I mean is basically this. Like, if num was 0, then this would return true. If num was 7, this would return false. And you might say, well, isn't 7 in the array? Yeah, 7 is in the array, but the index of the 7 here is 0. If num is 0, then we say, yeah, this has a 0 as an index. And then we do 1s at 0, and that's where we get the 7 there. Okay, so that's really, really important, but we do want it to be 0. Okay, so this should run the same way as what we had before. It's the same thing. This is not doing anything different, because it's saying if num is 0, return 0. This is saying if num is in 1s, but the only index this has is 0. So this is equivalent right now to saying if num is 0. And then the return 0, well, return 1s and num, that is 0. So really no difference between these two right now. Okay, so we do sort of want there to be a difference between these though. So basically the idea is that once we do our calculations, we sort of want to put it into the ones here. We want to memoize it, right? So basically, maybe we'll take this and we'll do something like this. So maybe we'll say something like const result is equal to this thing. Okay, so that's what we're going to be returning. I'll just put that in here, result. Let's run that, see if it works. Should. I mean, it's not any different than what we had before, really. Okay, and now what I want to say is 1s at num is assign the value of result. This is the memoizing, right? This is basically us saying we've calculated this result for this number. We now want to store that in here. That's basically the idea. So is that going to work, first of all? Yeah, it's working. Is it working the way we want it to? That's a good question. Well, let's try to figure that out. So basically, we'll take an example, I guess. Maybe we won't use as big of an example as we had before. Maybe we'll just go with like 5. Okay, so we've got 1, 0, 1. Okay, so how would this actually go through the algorithm here? So let's say we're starting with this, just the 0. So if num is in 1s, well, no, it's not. So we're going to move on from here. We'll say num and 1. Yeah, we get the 1 num count of 1, 0. Okay, so we get a 1 from this one, and then we're going to test 1, 0. We would not get a 1 from that, then we'll just test 1. We would get a 1 from that, then we'll test just the 0 from there. And then basically at that point, for each of these things, as they get executed, we're going to be storing these results, right? So basically now our 1s is going to contain something at index 0, at index 1, at index 2, and at index 5. So that the next time we encounter any of these things, it's just going to take it from the 1s array. It already will have the result at that index. So then it'll just say the next time it wants to run through, let's say the next one is 11, right? So we got 1, 0, 1, 1. Well, now we have 1s at 5 already stored in there, and we know it's going to be 2 because that's the result we would get in there. So then when we try to do this one, we'd say, okay, so if num in 1s, well, 11's not in there, so instead let's get this result, which has 1 count at 5. When it tries to do 1 count at 5, it'll say, okay, so is 5 in 1s? Oh, yeah, it is. So let's just return the 2 that we would have in that array. Okay, so basically it's not actually going to go through any of this stuff. It's going to say, okay, do we need to go any further than this? No? Okay, great, we're done. So that's memoizing. Okay, memoization, we're keeping track of previous results so that we don't have to recalculate them. And this should, at least in theory, run a lot faster than some of these previous ones. I realize maybe it's not as good for memory because we have a bigger array here. But the fact that we don't have to recalculate anything is basically better for time complexity. So it's a trade-off, and I mean that's the sort of trade-off that we're going to be used to seeing when it comes to things like backtracking, dynamic programming, and this memoization business. You know, we lose a bit of space complexity in order to gain some time complexity, or we lose space efficiency to gain time efficiency. That's basically what I mean. Anyway, is that passing all hidden tests? Let's find out. Let's try submitting that. Hopefully it's going to work for all these. There we go. Okay, nice stuff. So, there's one last thing I want to say for this one. I have a sneaking suspicion that there's a better way of doing this problem. I don't know what it is, but something about this just tells me there's probably a way to do this one that doesn't involve any loops or any recursion or anything like that. I just have a feeling that there is some kind of closed form, constant time formula for getting the results for this one. So I'm going to leave that as a challenge to you, the viewer. If you can figure out this way, this strategy, this hypothetical strategy that I have in mind, that would allow us to do this in constant time, and it doesn't have to be like a one-liner or whatever, but if we can find a way to do this in constant time, hey, let me know. I suspect it's possible, but I'm not sure. I think there's probably an integer sequence for this that's been identified, so we could take a look at the formulas in there. But anyway, I suspect there's a way to do it in constant time. I haven't figured it out myself. If anyone knows or figures it out, hey, let me know. I'd love to hear it. As for now, yeah, let's finish up with this one. I think, we've looked at a lot of different strategies here. We've learned something new potentially, so I'm satisfied with it. I hope you are too. All right, so let's go